Check it out now, y'all.
nanoHUB-U, online instruction.
Hi everyone, welcome to lecture 4 of Atoms to Materials. We're in week 5. Today we're going to talk about reactive interatomic potentials. These are force fields that allow us to do molecular dynamic simulations of processes that involve bond breaking and bond formation. These class of potentials have been developed over the last few decades, but it's been really in recent years that they have become very popular, in part because they allow us to do some very exciting simulations that cannot be done otherwise. So let's get to it. We're going to discuss some of the basic ideas that allow us to do these type of simulations. So in the lectures throughout the course, we've learned about different classes of interatomic potentials. Okay, we talked about potentials for metals, and there we talked about the importance of many body effects to characterize how the changing environment affects the bonding between atoms. We talked about the embedded atom model that works very well for most metals. We also talked about potentials for semiconductors, where the bonding is more covalent, okay, and directional. So in there we talked about the Stillinger-Weber potential as an example, and we saw that for Stillinger-Weber I needed to have 2-body and 3-body terms, okay? And the 3-body terms, these angular terms, make sure that we keep the bond angles at the distances that we'd like to have, and avoid open structures like diamond from collapsing into close-packed structures. And we also talked about interatomic potentials for molecular systems, for polymers and biological systems. And in those potentials, we have covalent interactions and non-bond interactions. The non-bond interactions are van der Waals and Coulomb, or electrostatics. And the covalent interactions have to do with bond stretch and angles and torsions and other sorts of terms. Now, one aspect of these potentials that we discussed is that I need to start with the connectivity, okay? I have to determine the connectivity before I start the simulation. The list of bonds need to be pre-described. Of course, the list of angles and the list of torsions needs to be predetermined, and they're fixed throughout the simulation. They cannot change. This is also important when we compute non-bond interactions, because if you remember, we discussed that these sums, there's exclusions for van der Waals or Coulomb interactions. If 2 atoms are bonded, then I don't compute van der Waals interactions between them, and I don't compute electrostatics between them. And if I did, the energies would be so gigantic that the system would be completely unstable. So can we relax these approximations? Can we make a potential where I don't have to pre-describe the connectivity, and I can allow for bonds to be broken and formed, kind of like it's done for EAM or Stillinger-Weber. In EAM, you can perfectly well break bonds, and in Stillinger-Weber the same thing. So can we think of a description that allows us to do all of these types of materials within the same framework, okay, so that I can do simulations that combine a ceramic with a metal, or a molecular material, the interface between a soft material and a ceramic or a metal. You can imagine that that's very attractive for many applications, and that will be we're very interested in being able to do this type of simulations. So the answer is that these potentials exist now, and they have been developed over the last few decades. and there's still a lot of progress and a lot of work to be done, but we're constantly making quite a bit of progress. In these potentials, the total energy is also described in terms of covalent or metallic interactions, electrostatics, and van der Waals. Okay, so same division as before. However, the details of how we do these calculations, how we compute these energies, is of course different. Okay, and that's what allows us to do chemical reactions. So there's a couple of features that I need to impose in a reactive potentials. First of all, no atom types. Okay, so the atoms should only be described by their element. I cannot have a sp2 carbon and an sp3 carbon. Only elements should be used. The partial charges on the atoms need to be calculated on the fly based on the environment. They should allow charge transfer during the simulation for a neutral atom to become an ion through a chemical reaction. And of course, I shouldn't be allowed to determine the connectivity, because that needs to be changed. So the connectivity, the bonds and the angles need to be computed on the fly as we do the simulation, so that bonds can be broken and formed. And that also means that I cannot have exclusions. I cannot, at least I cannot have hard exclusions. Okay, I cannot say, well, because these two atoms are bonded, then I'm not going to compute the van der Waals interactions between them, because, well, they can, that bond can be broken, and I need to start computing van der Waals interactions between those atoms. So those are some of the features or the constraints that one has in developing a reactive interatomic potential. And there's a key concept that has allowed our community over the years to develop these potentials very successfully, and that's the concept of partial bond order. Okay, so the bond order between atoms, okay, determines the chemical environment in those of the bonding between those two atoms, and this bond order is then determined in terms of the local environment around those two atoms. It's not just a pairwise relationship between the two atoms, but it depends on the two atoms and their environment. Okay, and if I know the bond orders, then I can compute the bond energy. So the idea is, given the atomic positions, given the environment, many body, I compute bond orders between atoms, and then from those bond orders, I can compute all the energy terms. Okay, this is an example of the bond order bond distance relationship in an interatomic potential called Reacts-FF, and it shows how the bond order grows, increases as I bring two carbon atoms together. Okay, the bond order becomes about 1, okay, at just over 1.5 angstroms or so. That's a sigma bond, okay, a single bond between carbon-carbon atoms. Then the bond can become 2 or so when you form the first pi bond, and then for even shorter distances, you'd have a double pi, a triple bond, okay. So there's this relationship, but let me stress once more that this is not a pairwise relationship, but a many-body relationship. The bond order between two atoms depends on their distance, but also on the local environment. Now, what characterizes different materials is how this bond order affects the bond strength. Okay, so if I have materials where the bond strength or the bond order doesn't weaken significantly as I add more bonds, okay? So if I have an atom and the more bonds I add don't cause a significant degradation of the bond strength, then that's going to be a material that favors close packing, okay? It's going to behave like a metal that tries to make as many bonds as possible. If the material penalizes strongly the creation of multiple bonds, then that atom is going to bond very judiciously with a few neighbors, okay? And in principle, we can only make one bond, like hydrogen, okay, H2. And so if you try to make another bond with a hydrogen atom that's already bonded, the strength of the ability to make those two bonds is very minimal. And so you minimize the energy by creating a single bond. So how the bond order and the bond energies depend on the number of bonds that an atom can make can determine whether you have a metal or a more covalent, metallic or more covalent type of interactions. So these ideas of bond orders and relationship between environment and bond orders can be traced back to the late 80s with Tursoff and Brenner in the early 90s, and have been used also more recently in Reacts-FF, which is a most widely used and most general interatomic potential we have today. So we have this relationship, okay, that based on the atomic configuration, we can compute the bond order between all atoms, and then with these bond orders, okay, after I calculate the bond orders, which depends only on geometry, then that affects my bond stretch, bond angle, bond torsions, okay? So if I have two carbon atoms and the bond order between them is about 2, then I know that that's a double bond. So I know that the torsions around that bond are going to be relatively strong, right? It's going to be hard to move around those that bond. And so the actual bond order between the atoms is the one that tells me what type of torsional potential I need to use, what type of angles I need to use. When I go from sp3 carbon with an angle of 109 to sp2 carbon with an angle of 120, that's the same thing. So the bond order between atoms, and the total bond orders on each atom, determines the potentials that I use for torsions, for angles, the equilibrium angles, the torsional barriers. And that's the way in which I can distinguish between the different bonding characteristics like sp2, sp1, or sp3 in a reactive force field, as opposed to having to use fixed atom types like as in non-reactive force fields. Now, as a bond order between two atoms goes to 0, if I break the bond, if I increase the distance, as that bond order goes to 0, all the covalent terms involving those two atoms also go to 0 smoothly, okay? So the angle between the angles involving that particular bond, let's say this particular bond is being broken, any angle involving that bond is going to go to 0. Any torsion around that bond is also going to go to 0. So smoothly, all the energy terms go to 0 if a bond is broken, and smoothly, a bunch of covalent terms are created if a new bond is formed, okay? Smoothly here is very important because we're interested in being able to do molecular dynamics, so I need to be able to take gradients of the total energy to get forces, so I cannot have discontinuous jumps in energies. And finally, there's a term that's called over-coordination or under-coordination penalties, and that's an overall energy of the atom that penalizes the atom if the total bond order on that atom is too big, and that makes sure that every atom makes as many bonds as it needs to make and not too many. Okay? So bond orders are the partial bond orders and continuous bond orders are at the heart of our ability to do reactive simulations. Now, Covalent interactions are not everything. We also need electrostatics and van der Waals, so let's talk about them a little bit. In the case of electrostatics, of course, the charges on the atoms cannot be fixed as we have assumed they were before, okay? Every time I have a chemical reaction, I need to allow for the chemical electrons to be transferred. For example, here's a picture of a silicon nitride amorphous sample. Of course, if I have an N2 atom, each atom will have 0 charge. In silicon nitride, there's going to be a little bit of charge transfer between silicon and nitrogen atoms. So I need to allow for that to occur. And the way this is done is through methods that are called charge equilibration methods. And essentially, what that allows you to do is to obtain the partial charge based on the instantaneous ionic positions. Okay, the way this is done is by minimizing a total electrostatic energy with respect to charges for a fixed set of atomic positions. So typically, the way these methods work is the following. There's a total electrostatic energy in the system that depends on the atomic positions, and this has two main terms. The first term here is the Coulomb interaction between atoms, okay? Remember, Coulomb is charge on one atom, charge on the other atom, and then some function of the distance. For point charges, this function is 1 over r. But we're going to see that that's not always the case in molecular dynamics simulations. But let's say that that's 1 over r. So that first term, it's a sum over pairs of atoms. It's the interaction between atoms. And the second term in the total electrostatic energy is essentially how much energy you have to give or win or take from an atom in order to change its charge. Okay, so it's a sum over all atoms of how much energy it costs to have that atom have charge Q sub I. Okay, we do a Taylor expansion up to second order. We have a term that's proportional to the charge and a term that's quadratic with the charge. The parameters that go there have to do with the electronegativity and the hardness of the atom that can be computed from the electron affinity and the ionization potential of each atom. So essentially the first term is the electrostatic interaction between charged atoms, and the second term is how difficult or easy it is to polarize an atom and transfer charge. And given a set of atomic positions, what we do is we find an optimal set of charges that minimizes this total energy. That's very similar to doing like cheap quantum mechanics. Okay, if you remember in density functional theory, within the Born-Oppenheimer approximation or in any ab initio calculation, we fixed the atomic positions and we would find the wave function, the electronic wave function that minimizes the total energy. This is the same thing, except that we're just trying to find the partial charges on the atoms that minimize the total energy. So these are two papers on how to do this. They're very similar in spirit, and in this way you can obtain charges on each atom that depend on the atomic position. So as the atoms move around and they break a bond or form a new bond, the charges will readjust instantaneously to this new environment. Okay. Now, we're talking about the interaction between two charges and what functions to use. So if I have two atoms that are far away, I can treat them as point charges. Okay. The clouds, of course, the the charge is not a real point. Okay, it's distributed over the wave function over a small region. But if they're very far away, I can approximate them as point charges, so the interaction is 1 over r. So as long as they're far away, it's 1 over r. If I bring them together and the charge distribution start overlapping, what you have is shielding. And what happens to the electrostatic energy is that it levels off, okay? It doesn't go to negative infinity as 1 over r, but it tapers off. It becomes a constant. And this is very important. This shielding is very important in reactive potentials because we do not have exclusions. So if we're going to compute the electrostatic energy between every pair of atoms, including bonded ones, if I have two atoms that are bonded, then their charge densities overlap, and 1 over r is not a good representation for their electrostatic potential. So I have to use shielded Coulomb to avoid this otherwise gigantic, let's say I have two atoms at this distance. Okay, the shielded energy will be a reasonable value. The unshielded 1 over r bare Coulomb would be enormous. Okay, so that's very important for reactive simulations where I don't have exclusions. How do we deal with shielding? Well, you can actually, if you assume the charge distributions have a shape, a finite size, you can do an explicit electrostatic calculation between these two charge distributions. Or in many reactive force fields, you use an empirical shielding function. Okay, so let me tell you one approach to do this that's used in many potentials. You define a shielded distance, okay, as a function of the real distance. So r prime is going to be the shielded distance, and r is the actual separation between these two atoms, and r naught is a characteristic distance, a characteristic size of these charge distributions. So if r, the distance between the two atoms, is very large compared to r naught, then r prime is equal to r, okay? Now, r prime, on the other hand, cannot be smaller than r naught, okay? So as the two atoms become very, very closer and closer together, this shielded distance r prime does not go to 0. It levels off and it goes to a finite value. When r is equal to 0, r prime is equal to r naught, okay? So then what I simply do is I compute the electrostatic energy with using 1 over r, but instead of using the real r, I use the shielded r, okay? And that makes sure that the potential does not go to negative infinity because r prime cannot go to 0, okay? So that's a simple, computationally efficient way of dealing with shielding. By the way, I'm not going to discuss this in detail, but van der Waals interactions also need to be shielded in reactive force field simulations because, of course, also the van der Waals interactions, regular van der Waals interactions are gigantic at bonding distances, okay? All right? So let me say a few words about parameterization of these potentials, okay? So when you're describing reactive potentials, of course, you need to parameterize them and teach these potentials on how hard or easy it is to break every bond, okay? So bond breaking curves. This is an example from Reactive of breaking a carbon-nitrogen bond, and what here we're comparing is Reactive with an ab initio quantum mechanical calculation. By the way, parameterizing reactive potentials from ab initio calculations is very useful because you can exercise individual terms in the potential energy very easily and single out individual terms in the potential. So what you do is you'd break every bond possible in the system. You would bend every angle like you see here for a nitrogen-oxygen-nitrogen angle, okay? And again, what you try to reproduce is the energy as a function of a bond angle. And here's the torsional potential in kcals per mole around a double bond between a carbon and a nitrogen atom, which, as you would expect, has a pretty decent torsional barrier, as you know from what we've learned. So again, you break every bond, you bend all the angles and the torsions. You typically use data for condensed phase systems to get van der Waals and information about charges to parameterize electrostatics. You typically can parameterize these potentials to describe very complex chemical reactions. In this plot, what I'm showing is the decomposition of an energetic material called RDX, and I'm showing 4 different decomposition pathways in the gas phase. And what I'm showing for each path is all the intermediate reactions during the decomposition and the associated transition states. Okay, so you can parameterize these for a bunch of intermediate products, intermediate components, but also very importantly, if you're interested in chemical reactions, of course, is to parameterize the energy barriers between these reagents. So that can be done as well. Okay, so having these reactive potentials enabled a very interesting class of simulations that were not possible up to that point. So for example, we used Reacts-FF to look at the chemical reactions in energetic materials induced by shock waves, and really looking at shock-induced condensed phase reactions for the first time. And we found some very interesting non-equilibrium chemical reactions happening very early, right behind the shock front. That were surprising. We also used reactive force fields to look at thermal-induced decomposition of these reactive materials, and really involving multimolecular reactions, very different from what you'd see in the gas phase. And we could see all the way to the formation of the final products, small molecules, big carbon clusters. So lots of exciting physics that were enabled by these type of force fields that would be very hard, even today, would be very hard to do with quantum mechanical approaches. So just to finish, let me point you to some references about on reactive potentials. The first 2 are the class of potentials called REBO, reactive empirical bond order potentials, and the last references are on Reacts-FF, which is a generally applicable reactive force field that covers a large piece of the periodic table. You can see there the first paper by Adri Van Duyng and collaborators at Caltech. And Adri Van Duyng and his group in Penn State continue to develop these potentials. All right, so thank you very much, and I'll see you in the next lecture. Bye.